Our comparative story begins in 2017, a time when the idea of interstellar visitors was still in the realm of theory, more a mathematical possibility than an observational reality. Scientists, through complex models, had calculated that based on the density of stars and planetary systems, there should be trillions of objects like comets and asteroids ejected from their home systems wandering the Milky Way. They form an invisible population, a river of exiles flowing between the stars, an integral component of the galactic ecosystem. Logically, occasionally one of them should pass through our solar system. But occasionally, on a cosmic scale, can be a very long time. We had looked, but we had never found one. The sky remained silent, a silence that led us to believe we were an isolated island, until the night of October 19th, 2017. On the summit of the Haleakala volcano in Hawaii, under one of the clearest night skies in the world, a telescope named Pan-STARRS-1 was performing its duty. Like Atlas, it is a sentinel, an automated survey system designed to scan the night sky, searching for moving points of light, especially asteroids that might come close to Earth. And on that night, among the countless images taken within the terabytes of data processed by computer clusters, the software flagged an extremely faint point of light. A point of light that didn't seem to belong, an anomalous signal in a sea of data, a glitch in the cosmic matrix. Astronomer Robert Varick, while reviewing the findings of that night, was the first to notice the anomaly. As he reviewed the data, he saw an object moving at an incredible speed. Initially, like any other discovery, it was considered a common asteroid and given a temporary designation. A new entry in a long catalog, nothing remarkable. But as Varick and his colleagues began to calculate its orbit, a sense of confusion began to set in. The numbers didn't add up. This object was not moving like anything they had ever seen in the solar system. Its orbit wasn't just hyperbolic. It was extremely hyperbolic. Its eccentricity, a number that describes the openness of an orbit, was calculated to be 1.2, an unprecedentedly high number. Anything with an eccentricity greater than 1 is not bound by the sun's gravity. Its path was not an elongated ellipse. It was a perfect open curve, a path of no return, a sentence of permanent exile from our star. It came from a very strange angle in the sky, from the direction of the constellation Lyra, near the bright star Vega. Some early news reports even mistakenly said it came from Vega, but scientists quickly pointed out that even traveling at that speed, it would have taken hundreds of thousands of years to get here from Vega. And at that time, Vega was not in that position in the sky. It did not come from Vega. It came from the deep space between the stars, and it was hurtling through the plane of the solar system from above at a nearly perpendicular angle, a very atypical behavior for our own objects, which tend to orbit on the same plane. Its speed while in interstellar space before being accelerated by the sun was estimated to be about 26.3 kilometers per second, which is nearly 95,000 kilometers per hour. This speed was far too great for it to be a member of the solar system family. In that moment, astronomers around the world came to a stunning realization. This was no longer a theory. This was not a computer simulation. This was real. For the first time in history, humanity had definitively confirmed the existence of a visitor from interstellar space. This moment had been awaited for decades. A new door had been opened. Excitement spread quickly through the scientific community, but it was mixed with a breathtaking sense of urgency, an alarming realization. Because unlike 3I Atlas, which was discovered on its way in this object, was discovered after it had already passed its closest point to the sun and was on its way out of the solar system at a dizzying speed. It had made its closest approach to the sun on September 9th, more than a month before it was discovered. It had also passed its closest point to Earth on October 14th, just 5 days before we first saw it. It had slipped past us almost undetected, a ghost in the night. It was like realizing a strange guest was in your house only after they had already walked through the living room, picked something up from a table, and were heading out the back door. We had almost missed it entirely. All our knowledge of this historic object had to be gathered from a fleeting glimpse, from a fading silhouette, from its last photons of light before it vanished into the darkness. The window for observation was incredibly short. The entire astronomical world engaged in a race against time. A global observation campaign was launched. Every major telescope possible, from the Very Large Telescope in Chile to orbiting observatories like Hubble and Spitzer, had to drop their pre-planned schedules to point at this fading streak of light. They had only a few weeks before it became too faint to be seen even with our most powerful instruments. Every single photon of light collected was priceless. Every hour of observation was an opportunity that would never come again. Scientists worked around the clock, analyzing data in near real time, trying to squeeze every possible bit of information from this hasty visitor. Even radio telescopes like Green Bank were listening, trying to find any artificial signals, however unlikely. And since this was the very first visitor, it needed a special name. A name worthy of the discovery's historic stature. The astronomical community, through the International Astronomical Union, decided to honor the place of its discovery. The Hawaiian Islands, a place with a long history of navigating and exploring the heavens, where ancient Polynesian navigators used the stars to find their way across the vast ocean. They consulted with Hawaiian cultural experts and chose a name from the native Hawaiian language, Oumuamua. The name, when spoken, sounds melodic and mysterious. The apostrophe at the beginning, called an okina, represents a glottal stop, an important part of the language. It is made of 2 parts. Umu means to reach out, and mua, in this case, is repeated for emphasis, meaning first or in advance, often used to refer to a scout or a pioneer in a battle. Combined, Oumuamua carries a beautiful and poetic meaning, the first messenger from a distant place. This name was not a cold designation. It was an acknowledgement of its role. It wasn't just a rock. It was a messenger, the first scout from another world carrying a message from the wider universe. And just as the ancient Polynesian navigators had bravely crossed the Pacific to discover new islands, Oumuamua was also an explorer, having crossed the ocean between the stars. The name was a beautiful connection between 2 journeys of discovery, one on Earth and one from the stars. But the message this messenger carried was anything but clear. As scientists began to analyze the scarce data they had collected in that race against time, the story did not become clearer. It only became stranger. Every answer seemed to raise 2 new questions. The initial confusion quickly turned into a deep sense of wonder. This is where our story shifts from a historic scientific discovery into a cosmic detective film. And the first piece of evidence, the first clue to its strangeness, came from its light itself, from the way it flickered and faded as it tumbled through space, a ghostly dance that hinted at an impossible form. The legacy of Oumuamua was one of haste and questions, a fleeting encounter that left us with more confusion than clarity. The astronomical community learned a valuable lesson. To truly understand these visitors, we need to detect them earlier. And in the years that followed, sky survey technology continued to evolve. Systems like Atlas became more efficient, their algorithms smarter. And in the summer of 2025, that preparation paid off. A new visitor arrived. But this time, its greeting was not a hurried farewell. It was a polite announcement from a distance. The story of Three-Eye Atlas, as we know, began on July 1st, 2025, also in Hawaii, but with a different system, the Asteroid Terrestrial Impact Last Alert System. Like Oumuamua, it too was discovered by an algorithm, a faint point of light moving on an unmistakable hyperbolic orbit. News of a potential new interstellar object was quickly confirmed, but immediately scientists recognized a fundamental difference. The biggest difference was the timing. Oumuamua was discovered more than a month after it had already passed its closest point to the Sun. It was on its way out of the solar system at maximum speed. Three-Eye Atlas, in contrast, was discovered while it was still very far away beyond the orbit of Mars and on its way into the solar system. This was a complete game changer. It was no longer a desperate race against time. It had become a planned observation campaign. It was like not only realizing a guest was coming to visit, but receiving an email from them several months in advance, announcing their schedule. This gave astronomers a priceless gift they did not have with Oumuamua time. They had months, not weeks, to prepare and observe it in detail. They could plan observation campaigns on the world's largest telescopes. They could apply for time on Hubble and James Webb in advance, not in an emergency override. They could track it through its entire arc through the solar system as it approached, as it brightened, as it passed perihelion, and then as it slowly faded and departed. This was a golden opportunity, a cosmic laboratory delivered to our doorstep with a detailed instruction manual. The second difference, also clear from the beginning, was its very nature. From the very first follow-up observations, Three-Eye Atlas showed a faint, fuzzy halo around it. A coma. There was no ambiguity, no debate. While Oumuamua was a mystery, was it an asteroid or a comet? Atlas introduced itself clearly from the start. "I am a comet," it seemed to say. This clarity reshaped the entire approach of the scientific community. With Oumuamua, the main question was, what is it? A fundamental, bewildered question. With Atlas, the questions became much more sophisticated. What is this interstellar comet made of? How is it similar to and different from our own? What can we learn about its home from its chemical composition? The story had shifted from a mystery thriller to a scientific documentary of exploration. This contrast could not be clearer. Oumuamua arrived as a ghost, sweeping by in silence and leaving questions. Atlas arrived as an ambassador, announcing its arrival in advance and ready to be studied. One was the chaos of a surprise discovery. The other was the order of a planned scientific campaign. And it is the contrast between these two greetings that sets the stage for the entire story we will explore. A story about the balance between the known and the unknown, between the familiar and the strange. After the mysterious and hasty arrival of Oumuamua, the astronomical community was craving a reference point, a bedrock of familiarity against which to compare, a control case from another star system. And Three-Eyed Atlas arrived not as a puzzle, but as an answer. A clear, beautiful, and extremely detailed answer. To begin our in-depth comparison of these two visitors, we must first reconstruct in detail the portrait of the third traveler. We must understand what the norm looks like before we can truly appreciate the anomaly of Oumuamua. Understanding the normal is the only way to recognize the extraordinary. This is the portrait of the familiar, a classic comet from the stars, an open book ready to be read. Chapter 2. A familiar answer. The portrait of 3I Atlas. When 3I Atlas was confirmed as an interstellar visitor, the first question was answered almost immediately. It was a comet. The evidence was undeniable and perfectly consistent with our centuries of knowledge about these objects. It was an open book following every rule in the astronomy textbook. Let's start from its heart, the nucleus. Although we couldn't see it directly obscured by the brilliant halo based on the amount of gas and dust it was emitting, scientists estimated the nucleus of Atlas was a few kilometers in diameter, perhaps between 2 and 10 kilometers. This size is perfectly within the typical range for comets in our solar system, from small ones just a few hundred meters across to giants like Hale-Bopp with its 60-kilometer nucleus. Atlas sat in a very average, very familiar spot. It was a giant, dirty snowball, an ancient relic made of water, ice-dry ice, organic compounds, and rocky dust preserved in the deep cold of space. More importantly, it was not a strangely long and thin object. Observations of its brightness variations while present were very small, suggesting a fairly normal length-to-width ratio, perhaps 2:1 or closer. All signs indicated it had an irregular, lumpy shape, like a potato or a peanut, a common feature of most comets and asteroids formed from random accretion and gentle past collisions. Most importantly, it behaved exactly as a comet should. As it entered the solar system and began to feel the warmth of the sun, it awoke. The process of sublimation began vigorously. The ice on its surface turned directly into gas, releasing a huge cloud of gas and dust. It grew a distinct and rapidly developing coma. This fuzzy halo was the first irrefutable proof that it was an active comet. It was not a dry, inert rock like Oumuamua. It was a living, breathing world of ice. This halo grew to an enormous size at one point, larger than the diameter of the sun, a tenuous but majestic cloud full of molecules freshly released from a billion-year slumber. The existence of this coma brought a sense of relief to scientists. It confirmed that icy bodies, the dirty snowballs, are indeed the common type of interstellar traveler, just as the models had predicted. Borisov was not a fluke, and Oumuamua was truly something different. The universe, for the most part, still works according to the rules we already know. And then, as it drew closer, it grew tails. The solar wind, the stream of charged particles from the sun, blew against the coma, pushing gas and dust behind it, forming glowing ribbons that stretched for millions of kilometers. Observers were able to clearly see both characteristic types of tail, a classic sight for a great comet. First was the dust tail. It is made of heavier, micrometer-sized dust particles released from the nucleus as the ice sublimates. Because they are heavier, they are not strongly affected by the solar wind. Instead, they tend to follow the comet's orbit, but are pushed slightly away by the radiation pressure of sunlight itself. This pressure, though very weak, acts continuously over a large area, slowly pushing the dust particles away, forming a broad, curved tail that is usually white or slightly yellow from reflecting sunlight. The dust tail of Atlas was clear proof that it was releasing a large amount of solid material fragments from its lost home. Second was the ion tail. It is made of gas molecules that have been ionized by the sun's ultraviolet radiation, meaning they've been stripped of their electrons. These ions are now electrically charged, and they get caught by the magnetic field of the solar wind. Therefore, the ion tail always points perfectly straight away from the sun, like a cosmic windsock showing us the direction of the plasma flow from the sun at that moment. It often glows with a faint blue color due to the emission of ions like carbon monoxide. The existence of both of these tails in Atlas was a classic signature, irrefutable proof of its cometary nature. Everything fit the textbook: the shape, the size, the formation of the coma, the development of the two types of tails. 3I Atlas was a perfect example. It behaved like a tourist visiting a foreign country who speaks the local language fluently, following all the customs and rules. It did not hide its nature. It introduced itself clearly: I am a comet, and in that clarity, there is a profound beauty. It shows us that the laws of physics and chemistry, the same laws that created the comets in our solar system, are also at work in other distant star systems. It is an affirmation of the universality of nature. It's like hearing a piece of music composed in another galaxy. The melody may be new, but you still recognize the notes, the chords, the laws of harmony. 3I Atlas was such a piece of music. Its melody may have come from a strange place, but its structure, its very essence, was deeply familiar. It was a whisper from the cosmos telling us, you are not so different. What happens in your home also happens elsewhere, and that is a comforting message. It builds a bridge of understanding across the interstellar void, making the vast and alien universe feel a little closer, a little more like home. That is the portrait of the familiar, a messenger of ice and light, an open book that we could read and understand, a solid anchor before we face the greater mysteries. The morphological and behavioral familiarity of 3I Atlas provided a solid foundation. It was a classic comet. But classic does not mean boring. Within that familiarity, Atlas gave us one of the most spectacular displays of color ever observed from an interstellar visitor, a feature that turned it into an icon. We are talking about its brilliant blue color, a color that was not just a random reflection, but a chemical signature, a song sung by molecules under the sunlight. And most importantly, it was a song we could completely understand. To delve deeper into the portrait of Atlas, we must revisit this beauty, not just as an aesthetic phenomenon, but as another affirmation of the order of the universe. When 3I Atlas had its brightness outburst, its coma didn't just swell. It donned a cloak of deep turquoise blue, a vivid and intentional color glowing from within. As we now know, this was a rare sight, but not an unexplainable one. The answer lies in an elegant physical process called fluorescence, and the protagonist of that process is a humble yet powerful molecule, dicarbon C2. Let's reconstruct this chemical story in detail. Everything begins in the icy reservoir of the nucleus. Within the water ice matrix, countless organic parent molecules are trapped carbon-rich molecules like methane CH4 and acetylene C2H2. As the comet neared the sun, the process of sublimation released these parent molecules into the near-vacuum environment of the coma. Here they faced the relentless stream of radiation from the sun, especially the high-energy ultraviolet UV photons. These photons act like invisible scissors, cutting the stable chemical bonds of the parent molecules in a process called photodissociation. Methane is broken, acetylene is broken, creating a chaotic soup of unstable molecular fragments known as free radicals. In this soup, the carbon atoms once freed found each other. Two carbon atoms bonded, forming the dicarbon molecule C2. Therefore, dicarbon was not an original ingredient. It was a secondary product, a child born from the interaction of the comet's matter and the sun's energy. Once created, these trillions of dicarbon molecules began their quantum dance. Imagine each molecule is a tiny musical instrument, and the sunlight is the conductor. The dance begins with absorption. A photon of sunlight, usually in the yellow or red range, strikes a dicarbon molecule. If that photon has a precise amount of energy, a perfect match for the molecule's preference, its energy is completely absorbed. This absorption kicks one of the molecule's electrons up to a higher energy level, an excited state. The instrument has been tuned. This excited state cannot last. Nature always seeks the lowest energy state. Almost immediately after just a millionth of a second, that electron will fall back to a lower energy level. And as it falls, it must release the energy it absorbed. It does this by emitting a brand new photon of light. And here is the magic. Due to the unique quantum structure of the dicarbon molecule, the energy of this emitted photon is not the same as the one that was absorbed. The electron's fall has a very specific energy, height, and that height corresponds exactly to the energy of light in the green and blue range of the spectrum. So what was happening was a large-scale energy transformation. The coma was absorbing yellow and red light from the sun and re-emitting it as a symphony of blue light. The entire halo had become a giant natural fluorescent lamp. And because this process, called resonant fluorescence, is extremely efficient in the low-density environment of space, where molecules rarely collide to lose energy, the resulting light was brilliant. The blue of Atlas was not magic. It was a beautiful demonstration of the laws of quantum physics operating on a macroscopic scale. We have understood the mechanism behind the blue song, a quantum dance of trillions of dicarbon molecules transforming sunlight into a brilliant halo. The entire process from photodissociation to fluorescence strictly adheres to the known laws of physics and chemistry, and it is this very understanding that makes 3I Atlas such an important reference point. It is an explainable beauty. Use arrow up and arrow down to select a turn, enter to jump to it, and escape to return to the chat. Let's put this in the context of a direct comparison with Oumuamua. The biggest mystery of Oumuamua was that it had an unexplainable push without any outgassing. It challenged our understanding. Atlas, in contrast, exhibited spectacular phenomena, but every single one of them had an explanation within the current framework of science. Its brightness outburst, though intense, is a familiar phenomenon in comets explainable by ice eruptions or the breaking off of small fragments from the nucleus. And its blue color, though rare and beautiful, was created by a well-understood mechanism, one that has been observed in other solar system comets, like Comet Holmes or Comet Swan, albeit with different intensities and hues. Atlas did not break the rules. It was simply a spectacular example of those rules in action. It's like hearing a symphony by Beethoven. You may have never heard a performance with such power and emotion, but you still recognize the familiar structure, the melodies, and the harmonic rules. It was a uniqueness within the familiar. This fact is critically important. It reinforces the role of Atlas as an interstellar control case. It shows us that an object from another star system with a completely different history still obeys the same set of physical and chemical laws. The universality of nature was once again affirmed. It makes the anomaly of Oumuamua stand out even more. If an interstellar comet like Atlas can put on a spectacular but perfectly explainable show, then the silence and mysterious push of Oumuamua become even more perplexing. Atlas, by its very normalcy, has deepened the mystery of its predecessor. Furthermore, the fact that we could explain the blue of Atlas is also a testament to the power of our tools. Spectroscopy worked perfectly. Astrophysical chemistry models made accurate predictions. It gives us confidence. Confidence that when we face true mysteries like Oumuamua, the problem is not that our physical laws are wrong, but that we are perhaps missing a piece of the puzzle. Three-Eye Atlas, with its explainable blue song, became an eloquent affirmation. An affirmation that in a universe full of unknowns, there is still order, rules, and beauty that we can fully understand and appreciate. It was a gift of clarity, a cosmic piece of music that we could not only enjoy but also read its sheet music. And by reading that sheet music, we not only understood Atlas itself, but we also gained precious clues about the place where that music was composed, its lost home. This explainable beauty was not the end of the story. It was the door to an even deeper understanding. We have built the portrait of the familiar. Three-Eye Atlas, a classic comet, an open book, an affirmation of the universe's order. Now, it is time for us to leave that safe harbor and begin our journey into the land of the anomalous. Let's return to the first visitor, Oumuamua. We will begin to decode the three great mysteries that have turned it into a legend. And the first mystery, the first clue to its strangeness, came not from its chemistry or its orbit, but from the most basic thing of all, the way it glittered as it drifted in the dark night. Chapter 3. A Thorny Question. The mystery of Oumuamua's shape. The first and biggest problem when observing Oumuamua was that it was too far away and too small. Even with the most powerful telescopes on Earth and in space, it appeared only as a single point of light, a single pixel on an image filled with stars. We could not take a picture of it to see if it was round, square, or any other shape. So how can we possibly know the shape of an object we cannot see? The answer lies in one of the most fundamental yet powerful techniques in astronomy, photometry. Or more specifically, the analysis of a light curve. A light curve is simply a graph that plots the change in an object's brightness over time. As an asymmetrical object, like a potato-shaped asteroid, rotates, the amount of sunlight it reflects toward us will change. When its wide side faces us, it will look brighter. When its narrow side faces us, it will look dimmer. By measuring this variation, scientists can deduce two things: the object's rotation speed and relatively its shape. Imagine you are looking at a small mirror from a great distance in a dark room. If that mirror is round and spinning, the amount of light it reflects toward you will be nearly constant. Its light curve will be an almost flat line. But what if that mirror is shaped like a needle and it's tumbling end over end like a baton? When the long side of the needle faces you, it will reflect a lot of light. You'll see a bright flash. But when it turns and only the sharp tip faces you, it will reflect very little light. The point will almost disappear. Its light curve will have very high peaks and very deep troughs. The amplitude of this variation reveals the degree of the object's elongation, and that is precisely what astronomers observed from Oumuamua. As they continuously measured its brightness over several nights, they saw an extremely dramatic variation. Its brightness changed over a period estimated to be about 7 to 8 hours, consistent with the rotation of an asteroid. But the amplitude of the change was what was shocking. It would get brighter and then dimmer by a factor of 10. This brightness variation, a factor of 10, was greater than for any asteroid or comet we have ever observed in our solar system. For comparison, most asteroids have brightness variations of only a few tens of percent. The few most elongated asteroids we know of might have a brightness change of a factor of 3, meaning a length to width ratio of 3:1, but a factor of 10. This was completely unprecedented. To produce such a massive change in brightness, Oumuamua had to have an extremely unusual, extremely non-spherical shape. The computer models showed that to match the data, its length-to-width ratio had to be very large. Initial estimates suggested it was at least 5:1 or 6:1, but later analysis showed it could be up to 10:1 or even more. It was at least 10 times longer than it was wide. Picture that again. If it were as long as a football field, it would be only as wide as the halfway line. If it were as tall as a skyscraper, it would be only as wide as a car. This was a needle-like or cigar-like shape, a shape never before seen in nature for an object of its size, estimated to be a few hundred meters long. Asteroids and comets in our solar system, after billions of years of random collisions from all directions, tend to be worn down into more rounded shapes like pebbles in a river. A 10:1 ratio is a massive statistical anomaly. The first message that the glittering light of Oumuamua sent us was a message of morphological strangeness. This first messenger did not take the form of a familiar friend. It took the form of a stranger, a complete stranger, with a structure that challenged what we thought we knew about how natural objects are formed and evolve. The light curve of Oumuamua gave us an incredible clue, an object with an extremely elongated shape. But elongated can mean many things. Based on the initial data, the first and most iconic model was constructed by scientists and artists. That was the model of a long, solid object tumbling through space, the image of a cosmic cigar. Let's delve into this model, exploring its characteristics and the challenges it poses to our understanding of the universe. In the cigar model, Oumuamua is envisioned as an elongated cylinder or ellipsoid, perhaps up to 400 meters long, but only about 40 meters wide. A 10:1 ratio. Its color was determined to be a dark red, similar to many objects in our distant Kuiper belt, a color that suggests its surface has been processed by cosmic rays for a very long time. One of the interesting things about its motion was that it wasn't spinning around its shortest axis, which is the most stable way to spin. Instead, it appeared to be tumbling, chaotically rotating about multiple axes at once, like a book thrown into the air. This chaotic rotational state suggests it may have experienced a collision or some other violent event in the not-too-distant past. This image, a dark red 100-meter-long cigar tumbling silently through the solar system, captured the public's imagination and became the defining image of Oumuamua. It was fascinating, eerie, and completely alien. That alienness came from a very basic question. How could nature make something like this? Let's compare it to what we know. Most asteroids and comets in our solar system smaller than a few hundred kilometers have irregular shapes. We often describe them as looking like potatoes or peanuts. They have lumps and bumps, but their overall ratio of length, width, and height rarely exceeds 3:1. For example, the asteroid Eros, studied in detail by the Near-Shoemaker spacecraft, measures about 34 by 11 by 11 kilometers, a ratio of about 3:1. Comet 67P Churyumov-Gerasimenko, explored by the Rosetta spacecraft, has a shape like a rubber duck with two lobes connected, but its overall ratio is also not too extreme. The reason for these more rounded shapes is their collision history. Over 4.5 billion years, objects in the solar system have been constantly colliding with each other. These impacts, coming from all directions, randomly tend to wear down sharp edges, break off protrusions, and gradually shape objects into more balanced proportions. It's like pebbles in a river, which may start out sharp-edged, but after a long time of being tumbled around, they become rounder and smoother. So why wasn't Oumuamua like that? Why did it retain such an extremely elongated shape? Several natural formation scenarios have been proposed. One idea suggests it could be a fragment from a tidal disruption event. Imagine a larger body, perhaps a dwarf planet or a supercomet, passing too close to its parent star. The star's immense gravity could have torn that body apart. This shredding process can produce long, thin fragments, much like stretching a piece of taffy. Then one of those fragments was ejected from the star system. Another idea is that it could have formed in a very special environment, perhaps in a rapidly spinning protoplanetary disk, where material was stretched out during the accretion process. Yet another hypothesis is that it could be the result of a high-speed collision between two objects, where a tongue of material was ejected and solidified into a long shape. All of these scenarios are physically possible, but they all require a very specific and possibly quite rare chain of events. They don't explain why the very first visitor we ever met was the product of such a rare process instead of a normal potato. The existence of a cigar-shaped object in nature is not impossible, but it is very unusual. It is a statistical anomaly, and when scientists are faced with an anomaly, they must consider all possibilities, including the possibility that this cigar model might not be the only answer. The cigar model dominated our initial visualizations of Oumuamua, a powerful, iconic image, but one that posed thorny questions about its natural origin. But as scientists continued to analyze the light curve, they realized there was another possibility. The data didn't just say the object was long. It only said that the ratio between its longest and shortest axes was very large. And there is another shape that also fits that description perfectly, a shape that is perhaps even stranger. That is the model of an extremely flat object, a pancake, a disc, or even a thin shard. Let's go back to our mirror metaphor. A spinning needle will produce a large change in brightness, but a flat disk tumbling through space will do the same. When the flat face of the disk is toward you, it will reflect a large amount of light, creating a bright peak. When it turns and you see only its thin edge, the amount of reflected light will drop dramatically, creating a deep trough. The light curve produced by a tumbling disk can be almost indistinguishable from the light curve of a tumbling cigar. So, Oumuamua might not have been an object hundreds of meters long and a few tens of meters wide. It could have been an object hundreds of meters wide, but only a few tens of meters thick, or even thinner. Some later analyses, based on the way it was tumbling, even suggested that a flat pancake-like shape was statistically more likely than a cigar shape. This image, a dark red disk tumbling silently through the solar system, also raises big questions about its origin, but perhaps in a slightly different direction. How could nature create a cosmic pancake? Once again, scientists returned to the tidal disruption scenario. Imagine a comet or a dwarf planet passing too close to a large star or even a black hole. The extreme gravity could not only tear the object apart, but it could also flatten the fragments into disc-like shapes. Another scenario, as we discussed in the nitrogen shard hypothesis, is the process of erosion in interstellar space. An icy fragment, when constantly bombarded by small particles and radiation from all directions, could be naturally worn down into an increasingly flat shape over time, like a bar of soap being worn down with use. More recently, another interesting hypothesis has been proposed involving large porous dust aggregates. Perhaps Oumuamua was not a solid rock. It could have been an extremely light and fluffy collection of icy dust grains, like a giant cosmic snowflake. Such an object could be easily flattened by radiation pressure or other forces. Each of these possibilities has its own strengths and weaknesses, but they all point to one thing: the shape of Oumuamua, whether a cigar or a pancake, was an anomaly, a product of a process that might be rare or extreme. This uncertainty about its shape is an important part of the Oumuamua story. It shows the limits of our observational methods. With just a light curve, we cannot determine a unique three-dimensional shape. There is an inherent ambiguity. It's like seeing only a person's shadow and trying to guess what they look like. You can get a few ideas, but you can never be completely sure. And it is this very ambiguity, the existence of multiple strange possibilities, that has made Oumuamua such a fascinating object for scientific speculation. Whether a cigar or a pancake, the first clue was firmly established. Our first visitor had a completely alien form, but its strangeness did not end there. It also lay in its very essence, in its contradictory silence as it faced the heat of the sun. We have just contemplated the mystery of Oumuamua's shape, a riddle written in glittering light and shadows. But its strangeness was not just in its form. It was also in its essence, in its absolute silence. To truly understand how profound that silence was, we need a reference point. We need to listen to the sound of a normal interstellar comet as it awakens. Let's put Oumuamua aside for a moment and return to our third traveler. Let's listen to its symphony. Chapter 4. A dialogue of silence and voice. The story of Three-Eye Atlas is a story of a spectacular awakening. As it entered the solar system from the cold of interstellar space, it was a dormant iceberg, a frozen memory. But as it crossed the orbit of Mars and drew closer to the sun, the warmth began to stir the sleeping giant. This process, called sublimation, is the voice of a comet. It's how it communicates with the universe. Its icy surface, when heated, does not melt into liquid water. In the vacuum of space, it transforms directly from a solid to a gas, an explosive transition. And Atlas spoke very loudly. It experienced a violent outburst of activity. Its surface, perhaps due to the exposure of pockets of volatile ice, began to erupt a huge amount of gas and dust into space. The first consequence of this voice was the formation of the coma, a giant halo of gas and dust growing rapidly, enveloping the invisible nucleus. At its peak activity, the coma of Atlas was hundreds of thousands of kilometers in diameter, larger than the biggest planet in the solar system, Jupiter. It had transformed a rock a few kilometers wide into a structure on the scale of a planet. This halo was not just a passive cloud. It was a dynamic environment, a mini chemical factory, where the molecules released from the ice interacted with sunlight, creating new molecules and emitting their own light, including its characteristic brilliant blue. This was the voice of Atlas, a visible glowing halo announcing its presence for all to see. The second consequence was the formation of the tails. The solar wind and radiation pressure blew material from the coma backward, creating two cosmic ribbons that stretched for millions of kilometers. The dust tail, made of solid particles, curved along the comet's orbit like a trail of smoke left behind a ship. It was a visible record of the path the comet had taken. The ion tail, made of ionized gas, pointed straight away from the sun, a glowing cosmic compass. These tails were the most spectacular manifestations of cometary activity. They were Atlas's declarations, visible from a great distance. This entire process, sublimation, coma formation, tail development, was a symphony of physics, a predictable, familiar, and incredibly powerful sequence of events. 3 Atlas arrived and sang its song loudly. It told us in the language of ice and dust that it was a comet, a living entity interacting with its environment. Its voice was an affirmation, a solid reference point. Hold the image and sound of this symphony firmly in your mind. The image of a giant halo, the sound of ice eruptions, the feeling of energy being released, of a constant transformation. Because only when we have truly listened to this voice can we begin to feel the depth and the astonishment of its opposite, the silence. We have just listened to the symphony of Atlas, a resounding sound of sublimation of ice turning to gas. Now it is time to return to the first visitor. Let us return to Oumuamua, and in the contrast, we will hear something even more powerful than a symphony. We will hear the silence, an absolute contradictory silence that lies at the heart of the mystery. Let's set the scene clearly. When Oumuamua passed through the solar system, it wasn't just near the sun, it passed extremely close. At its perihelion, it was only about 38 million kilometers from the sun. This distance is even closer than the orbit of Mercury, our innermost planet. At that distance, the temperature on its surface on the illuminated side was estimated to have reached over 300 degrees Celsius. Hot enough to melt lead. Under such scorching heat, any type of ice we know, water ice, carbon dioxide, ice carbon monoxide ice, should have sublimated violently. There is no physical model that allows a dirty snowball to exist in such a furnace without vaporizing. Scientists fully expected Oumuamua to behave like a highly active comet. They searched with every instrument they had for the signs of a coma and a tail. They found nothing. Ground-based optical telescopes stared at it, trying to detect any faint halo of dust. The result was zero. It was just a sharp point of light, but perhaps it was outgassing transparent gas without any dust. This is where one of our most powerful instruments came into play, the Spitzer Space Telescope. Spitzer was a space observatory designed to look at the universe in infrared wavelengths. It was extremely sensitive to the thermal signatures of molecules. Molecules like carbon monoxide CO and carbon dioxide CO2, when released from a comet, will absorb and re-emit sunlight at very specific infrared wavelengths. Spitzer was built precisely to detect these fingerprints. In November 2017, scientists pointed Spitzer at Oumuamua for many hours, a final attempt to hear its chemical breath. The result was one of the strongest pieces of negative evidence in this story. Spitzer detected no sign of carbon monoxide or carbon dioxide. This absence was so precise that scientists could place an extremely stringent upper limit on the amount of gas Oumuamua could be outgassing. The amount of gas, if any, was too small, thousands or even millions of times less than a typical comet at the same distance. Oumuamua was chemically inert. It was a breathless visitor. This was extremely puzzling. It created a deep contradiction. If it was a comet made of ice, why wasn't it active? One hypothesis suggested it might be covered by a thick organic crust, an armor created by billions of years of irradiation, which insulated the ice inside. This is possible, but that crust would have to be incredibly thick and durable to withstand such scorching heat without cracking. So if it wasn't a comet, then it must be an asteroid, a dry rock. This seems to solve the problem of the silence, but it opens the door to another even bigger problem. As we know, models suggest that interstellar comets should be hundreds of times more common than interstellar asteroids. Why was the very first visitor we ever met the incredibly rare one? Furthermore, its dark red color is consistent with a surface rich in organic compounds, a feature often seen on icy bodies in the outer edges of star systems, not rocky asteroids from the inner regions. The silence of Oumuamua was a silence full of contradictions. Every explanation seemed to lead to a dead end, and it was this very silence that made the final clue, the anomalous push, all the more shocking. We are at the heart of the dialogue. On one side, the resounding voice of 3I Atlas, a symphony of sublimation, a clear affirmation of its cometary nature, and on the other, the profound silence of Oumuamua, a silence that was not an absence of sound, but a contradictory message. This silence forced scientists to face a fundamental dilemma, a fork in the logical path where both directions seemed to lead to a wall. Was it an asteroid or was it a comet? Let us analyze these two paths carefully step by step. Path 1. Oumuamua was a comet. This hypothesis has a major plus: it fits our models. Scientists predict that most interstellar objects ejected from their star systems should be comets, as they form in the outer regions where gravity is weaker. The first visitor being a comet is statistically perfectly reasonable, but this hypothesis immediately runs into a huge problem: the silence. If it was a dirty snowball, why didn't it melt under the scorching heat of the sun? Why did our most sensitive telescopes detect not even a whiff of gas or dust? One possibility is that it had an extremely thick and durable organic crust that insulated the ice inside. This crust would have been formed over billions of years of irradiation in interstellar space. This could explain its dark red color. But how resilient would that crust have to be to not crack when the surface temperature rose above 300 degrees Celsius, and if there were a few small cracks venting gas? Why did Spitzer see nothing? The question remains. This path leads to a strange comet, a comet that doesn't behave like any comet we've ever seen. Path 2. Oumuamua was an asteroid. This hypothesis also has a major plus. It perfectly explains the silence. If it was a dry rock made of stone and metal, there would be no ice to sublimate. No ice, no coma, no tail. Problem solved. But this path leads to a series of other thorny problems. Problem 1 is probability. As we've said, models suggest that interstellar asteroids should be hundreds or even thousands of times rarer than interstellar comets. Why was the very first visitor? We met an extremely rare object. It's like randomly drawing a card from a deck of the problem 2 is the color. The dark red of Oumuamua is more consistent with a surface rich in organic compounds a feature often seen on icy bodies in the outer edges of star systems like Kuiper Belt objects, and not the typical gray color of rocky asteroids from inner regions. And the third and biggest unignorable problem is the push. An asteroid, a barren rock, has no mechanism to generate its own thrust. It must obey the laws of gravity perfectly. But Oumuamua did not. It accelerated inexplicably. So if you say it's an asteroid, you can explain the silence, but you absolutely cannot explain the push. This is the core contradiction, the heart of the Oumuamua puzzle. It behaved like a comet in terms of its motion had non-gravitational thrust, but it looked like an asteroid in terms of its appearance had no coma. It seemed to be something in between, a hybrid type of object we had never seen before, or something else entirely. Both logical paths, based on what we know, lead to a dead end. The dialogue between silence and voice did not lead to a reconciliation, but to a confrontation. And this confrontation forces us to continue our comparative journey to the final and most decisive element, their dance. We have seen the deep contradiction in the nature of Oumuamua, an object that behaved like a comet, but looked like an asteroid. Now we come to the final and most decisive element in this comparison, their dance through the solar system. The journey of an object through space is governed by one of the most fundamental and well-understood forces of the universe, gravity. By observing an object's motion, we can test whether gravity alone is sufficient to explain its journey. Let's begin with our reference point with the dance of order. Chapter 5, The Dance of Gravity and the Invisible Wind. When 3I Atlas was discovered, scientists began a meticulous tracking process. Hundreds of observatories around the world continuously measured its position in the sky, creating a huge data set of its journey. With this data set, the next job was to build a model. Astrophysicists use Newton's laws of motion and the law of universal gravitation to create a hyper-accurate computer model of the solar system. This model includes not only the immense gravity of the Sun, but also the subtle pushes and pulls from all the planets from giant Jupiter to tiny Mercury, and even some of the largest asteroids. Then they dropped 3I Atlas into this model. They input its initial observed position and velocity and let the model run. The computer would calculate step by step the path the comet must follow if only gravity were acting on it. The result was a perfect hyperbolic orbit, a path predetermined by mathematics. The final and most important step was the comparison. They compared the theoretical orbit generated by the model with the actual orbit observed by the telescopes. And for 3I Atlas, the result was a near-perfect match. Its observed positions lay exactly on the path predicted by the gravitational model. There were no significant deviations. Of course, the scientists did not stop there. They knew that Atlas was an active comet, and its outgassing must produce a small thrust, a non-gravitational acceleration. So they added another factor to their model, a small thrust modeled after the outgassing of a typical comet. And when they did this, the match became even more perfect. The tiny remaining discrepancies between the model and the observations vanished completely. The small push from Atlas's outgassing perfectly explained its motion. And most importantly, the amount of gas needed to create that push was perfectly consistent with what they observed from its coma and tail. Everything was explainable. The dance of Atlas was a predictable dance. It was a perfect example of celestial mechanics in action. It moved like a cosmic bullet, its trajectory bent by gravity and influenced slightly by the recoil from its own outgassing engine. There were no surprises, no unexplainable deviations. It was an eloquent affirmation that even for a visitor from another star system, the physical laws we know still hold perfectly true. This precision, this predictability is extremely important. It gives us a solid foundation. It shows that our tools and models are accurate. When an object behaves normally, we can describe it perfectly. The success in modeling the orbit of Atlas reinforced our confidence, and it was this very confidence that made what they found when they applied the same method to Oumuamua all the more shocking. The dance of Atlas was a graceful and predictable waltz, governed by the familiar laws of gravity and outgassing. It had reinforced our confidence in our models. Now let's apply the same method, the same rigor to the first visitor. Scientists took all the observations of Oumuamua's position, especially the extremely precise measurements from the Hubble Space Telescope as it was on its way out. They also built a hyper-accurate gravitational model and calculated the path Oumuamua must follow, and then they compared. And this time, they did not match. The deviation was tiny, but unmistakable. As astronomers at the Hubble Space Telescope continued to track Oumuamua, they discovered that it was veering off the path predicted by gravity. More specifically, it was not slowing down as much as it should have. As an object flies away from the sun's gravity acts like an invisible rubber band, pulling it back and slowing it down. Oumuamua was being slowed, but not enough. It was moving slightly faster, just a little bit, than gravity alone could explain. It was as if a gentle, constant, invisible push was pushing it from behind, counteracting the pull of the sun. This non-gravitational acceleration was extremely small. It was only about 0.1% of the sun's gravitational acceleration. To visualize it, imagine you are driving a car on a straight road and you turn off the engine. You expect the car to gradually slow down due to friction, but your car isn't slowing down that quickly. It seems to be maintaining its speed a little better, as if there's a gentle wind blowing from behind. You can't see the wind, but you can measure its effect. That is precisely what scientists saw with Oumuamua. They could not see the cosmic wind pushing it, but they could measure its effect on the orbit. The immediate question was, is this deviation really significant, or is it just a measurement error, an uncertainty in the data? This is where the importance of the Hubble Space Telescope comes in. Because Hubble is in space, it can measure the position of Oumuamua with a precision no ground-based telescope can match. The research team, led by Marco Micheli, analyzed the data with extreme care. They checked for every possible source of error. Could it be the radiation pressure of sunlight? Yes, but that effect was too small for a rocky object and was already accounted for. Could it be errors in the gravitational model? No, this model has been verified with thousands of other objects. After eliminating every possible source of error, they came to a firm conclusion. The non-gravitational acceleration was real, and it was extremely statistically significant at a level of 5 sigma. In particle physics, a 5 sigma level is the gold standard for claiming a discovery, like the detection of the Higgs boson. It means the probability that this result is just a random statistical fluctuation is extremely low, only about 1 in 3.5 million. In other words, they were virtually certain that a mysterious force was acting on Oumuamua. This was the aha moment in the Oumuamua story. It transformed a strange object into a truly anomalous one. It was no longer just a weirdly shaped rock. It was a weirdly shaped rock that was moving on its own in an unexplainable way. For a comet, this would be no surprise. The push from outgassing is a perfect explanation. But Oumuamua was silent, and it is this lethal combination, the undeniable existence of a push and the complete lack of any obvious explanation for that push that opened the door to the most audacious hypotheses. The dance of Oumuamua was not a predictable waltz. It was a ghostly dance led by an invisible partner. We are faced with a seemingly unsolvable contradiction. The data from Hubble shows with certainty that Oumuamua was being pushed by a mysterious force beyond gravity. The most natural and familiar explanation for such a push for a small body in the solar system is the outgassing of a comet. Jets of gas and dust erupting from the surface, acting like tiny rocket engines. So why couldn't scientists simply conclude that Oumuamua was an outgassing comet even if we couldn't see it? The answer lies in the numbers. When we delve into the physical calculations, the wall of contradiction becomes higher than ever. Astrophysicists can do a reverse calculation. Based on the observed level of non-gravitational acceleration, they can calculate exactly how much thrust was needed to produce it. And from that thrust, they can calculate the amount of material gas and dust the comet must have been ejecting per second. When they performed this calculation for Oumuamua, the result posed a major problem. To produce the measured push, Oumuamua would have had to eject a significant amount of gas and dust, not a few molecules but kilograms of material per second. This amount of material, when released into space and illuminated by the sun, would undoubtedly create a coma, and this is where we return to the observations. Scientists didn't just say, "We didn't see a coma." They did something much more precise. They placed an upper limit on its existence. They analyzed the deepest images from Hubble and Spitzer and calculated that if any coma existed, it had to be fainter than a certain threshold. If any dust existed, it had to be less than a certain mass. And when they compared these two numbers, the contradiction became starkly clear. The amount of gas and dust needed to create the push was much, much greater than the maximum amount of gas and dust that could have been there without being detected by our telescopes. In other words, to push itself like that, Oumuamua would have had to produce a giant, brilliant coma. A coma we would have certainly seen even with amateur telescopes. But it didn't have one. This is a direct contradiction, an impossible equation. It's like hearing the engine of a racing car accelerating. But when you look, you see no smoke coming from the exhaust. Some have tried to resolve this contradiction. Maybe it was only ejecting very large, hard-to-detect dust grains. Calculations show this is inefficient at producing thrust. Maybe it was only ejecting gas without any dust. This rarely happens, as escaping gas always carries some dust with it. And even if so, as we've seen Spitzer detected, none of the common gases. Maybe its shape affected how we saw the coma. Possibly, but not enough to explain its complete absence. Every attempt to reconcile the push and the silence with the mechanism of cometary outgassing has failed. It cannot be both a vigorously active comet to push itself and a completely inert object to remain undetected. It cannot be both at the same time. This is what forced scientists to search for out-of-the-box explanations. If it wasn't the outgassing of a comet, then what was the invisible wind pushing Oumuamua? Was it a completely new type of matter like hydrogen ice? Was it a nitrogen ice fragment, venting transparent nitrogen gas? Or was it something else? The failure of the simplest explanation opened the door to the most extraordinary ideas. We have reached a logical dead end. The simplest and most familiar explanation, the outgassing of a comet, does not seem to fit the observational evidence. The push was real, but the coma was invisible. When a familiar explanation fails, science does not give up. It gets creative. Scientists begin to ask what-if questions. What if it wasn't a normal comet? What if it was made of a type of matter we had never seen before? This is where we enter the world of out-of-the-box explanations. Chapter 6. The explanations, natural or artificial. The first and most important effort is to try and find a natural explanation, no matter how strange. The leading natural hypothesis attempts to solve the biggest contradiction: how to have a push without a coma. The answer might be that it was venting a gas that was invisible. The first hypothesis, as we've mentioned, is the hydrogen comet. Proposed by scientists Daryl Seligman and Gregory Laughlin, this idea suggests Oumuamua could be made of solid hydrogen ice. Hydrogen is the most common element in the universe, and theorists believe that hydrogen icebergs could form in the ultra-cold cores of giant molecular clouds. The strength of this hypothesis is that it elegantly solves the problem. When hydrogen ice sublimates, it turns into molecular hydrogen gas H2, which is almost completely transparent and very difficult for our telescopes to detect. So in this scenario, Oumuamua was indeed a vigorously active comet, venting a huge amount of invisible hydrogen gas to create its push. It was the ghost of a comet. However, this hypothesis also has fatal flaws. Hydrogen ice is extremely volatile. It would sublimate even under the faint starlight of interstellar space. Calculations show that an iceberg the size of Oumuamua could not have survived a journey of hundreds of millions of years. It would have completely evaporated like an ice cube left in the desert. For this hypothesis to be true, Oumuamua would have to be extremely young and from a very nearby system, which seems inconsistent with other data. This leads to the second leading natural hypothesis, a somewhat more robust one, the nitrogen shard. Proposed by Alan Jackson and Stephen Desch, this idea suggests Oumuamua was a fragment broken off from the surface of a Pluto-like planet in another star system. Let's analyze this. We know that Pluto's surface is covered in solid nitrogen ice. When nitrogen ice sublimates, it also turns into transparent nitrogen gas, solving the problem of the invisible coma. At the same time, unlike hydrogen ice, nitrogen ice is much more durable and could easily survive a long journey through interstellar space. This hypothesis even explains the strange shape. The scientists calculated that as a nitrogen ice fragment travels through space, the slow erosion from cosmic rays and interstellar dust would tend to flatten it over time, like a bar of soap being worn down. This is perfectly consistent with the pancake-like model of Oumuamua. So here we have an almost perfect story, a fragment of an exopluto made of nitrogen ice eroded into a pancake shape, flew into our solar system, and vented transparent nitrogen gas to create its push. Every piece of the puzzle seems to fall into place. However, this hypothesis also has its own challenges. First, it would require an extremely large number of Pluto-like planets out there for us to have a chance of encountering a fragment from one. Some scientists argue this number is unrealistic. Second, it also requires a certain coincidence in the timing of the erosion to produce such a flat shape. Despite this, the nitrogen shard remains one of the most favored and most discussed natural explanations. Both of these hypotheses are testaments to the creativity of science. They show that the universe may contain types of objects we have never imagined: ghost comets or icy legacies from shattered worlds. But for some scientists, these explanations still seem too contrived, requiring too many special conditions. The natural hypotheses, though creative, still have weaknesses and require rather special conditions. This incompleteness has led some scientists to ask, are we missing another possibility? Is there a simpler, albeit more extraordinary explanation that could solve all the mysteries at once? This is where we come to the most high-profile and controversial hypothesis, an idea that took the discussion about Oumuamua out of astronomical journals and onto front pages around the world. We will examine it carefully and objectively, not as a truth, but as a possibility, an important thought experiment. This is the bold hypothesis of Avi Loeb. Avi Loeb, a prominent theoretical physicist and former chair of the astronomy department at Harvard University, approached the problem from a different angle. He applied the principle of Occam's razor, a philosophical rule that states the simplest explanation, the one that requires the fewest assumptions, is often the correct one. He argued that instead of having to invent new types of natural objects we've never seen, like hydrogen icebergs or nitrogen shards, to explain each mystery separately, is there a single explanation that could simultaneously solve all three core mysteries of Oumuamua: the strange shape, the absolute silence, and the invisible push? And the explanation he proposed, as laid out in his book, Extraterrestrial, is that Oumuamua may not have been a natural object. His hypothesis is that its characteristics are most consistent with a technological product. It must be stressed again, this is a speculative hypothesis put forth by a respected scientist to provoke dialogue, and it is not accepted by the majority of the scientific community. But let's examine the logic behind it. Loeb does not suggest it was a crude spaceship. Instead, he proposes a more specific possibility: a light sail. A light sail is a technology that we humans are also developing, for example, in the Breakthrough Starshot project. The idea is to create an extremely thin, light, and highly reflective sheet of material. When launched into space, the pressure from the photons of sunlight itself or a powerful laser beam would push it along, much like wind pushes a sailboat. This is a fuel-free propulsion method capable of reaching enormous speeds, ideal for interstellar journeys. Now let's see how this hypothesis solves the three mysteries of Oumuamua. Mystery number 1: the shape. A light sail, to be effective, must have a very large area-to-mass ratio. This means it must be extremely thin and wide. Its shape would be a sheet, a disc, or a flat shard. This is perfectly consistent with the pancake-like model, one of the leading possibilities inferred from the light curve. Mystery 2: the silence. A light sail is made of solid material, possibly metal or composite materials. It contains no ice. Therefore, it would not outgas, would not create a coma or a tail, even when very close to the sun. It would be chemically completely silent. Mystery number 3: the push. This is the strongest point of the hypothesis. The anomalous push of Oumuamua is no longer a mystery. It is the object's very design purpose. The push comes not from within, from outgassing. It comes from without. It is the push from the radiation pressure of sunlight acting on a thin light surface. Loeb's calculations showed that if Oumuamua were a thin sheet less than a millimeter thick, the sun's radiation pressure could produce the exact level of non-gravitational acceleration that was observed. From this perspective, the three biggest anomalies of Oumuamua are no longer anomalies. They become logical consequences of a single explanation. This simplicity is what Loeb finds compelling. He does not say it is this for certain. He only says that based on the evidence we have, the hypothesis of a technological relic is a possibility that should be considered seriously alongside the other natural hypotheses. The story of Oumuamua through this lens has become a Rorschach test for the scientific community, a test of our openness to the extraordinary. The hypothesis of a technological relic from Avi Loeb, while fascinating and solving many problems, immediately ignited an intense and incredibly important scientific dialogue. It is crucial to understand science does not operate on single declarations, no matter how respected the scientist. Science is a process of skepticism, of verification, and of finding the explanation that best fits all the evidence. And the vast majority of the astrophysical community, while acknowledging the strangeness of Oumuamua, maintains a deep skepticism toward the artificial origin hypothesis. Let's listen to these counterarguments. The main criticism of Loeb's hypothesis is based on one of the foundational principles of the scientific method, a saying popularized by the astronomer Carl Sagan: extraordinary claims require extraordinary evidence. The claim that we have detected a technological product of an extraterrestrial civilization is perhaps one of the most extraordinary claims humans can make. Therefore, the burden of proof is extremely high. Meanwhile, the evidence we have for Oumuamua is extremely scarce and ambiguous. We only had a few weeks of observation of a faint point of light. We do not have a detailed picture. We do not have a high-resolution spectrum. We did not detect any radio signals. The critics argue that with such a limited data set, jumping to an extraordinary conclusion is premature and not scientifically robust. They point out that the history of astronomy is full of mysteries that initially seemed extraordinary, but were later explained by new natural phenomena. For example, pulsars, rapidly spinning neutron stars, when first discovered in 1967, emitted such regular radio signals that they were nicknamed LGM-1 for Little Green Men. But they were later proven to be an entirely natural phenomenon. Gamma-ray bursts, the most energetic events in the universe, were also a huge mystery for decades before we understood them. The view of the majority of the scientific community is this: Oumuamua is most likely also a natural phenomenon, just a type of phenomenon we have never seen before and do not yet fully understand. They argue that the current lack of a perfect natural explanation is not evidence for an unnatural one. It is simply a sign that our knowledge is still incomplete. The preference for natural explanations, known as methodological naturalism, is a cornerstone of science. We must exhaust every possible natural explanation, no matter how unlikely they may seem, before we can begin to seriously consider unnatural possibilities. This dialogue is not an argument. It is a healthy and necessary debate. One side, like Avi Loeb, is pushing us to be more open, to be willing to consider possibilities we previously considered taboo. The other side, representing the majority of the community, is calling for caution, for rigor, and for adherence to the proven scientific method. Both of these viewpoints are valuable, and both are necessary for the progress of science. Ultimately, the story of Oumuamua has no conclusion. It remains a mystery waiting to be solved, and perhaps the answer will not come from debating Oumuamua further, but from finding the next visitors. But whatever the final explanation may be, Oumuamua has forever changed the game. It has forced us to confront the big questions, and it has shown us that the universe still has countless surprises in store. We have traveled through the maze of hypotheses and listened to the lively scientific dialogue surrounding the mystery of Oumuamua. And perhaps we will never have a final answer to that riddle. But perhaps the purpose of these visitors is not to bring us final answers about themselves. Perhaps their purpose is to teach us lessons about the universe and about our own journey of discovery. In this chapter, we will take a step back, look at the bigger picture, and contemplate the three profound lessons that these two visitors have left behind. Chapter 7: A Lesson in Diversity. Let us begin with the lesson of the familiar. The lesson from 3i Atlas. After the confusion and the thorny questions left by Oumuamua, the arrival of 3i Atlas and its predecessor, 2i Borisov, was like a gentle rain shower after a hot summer day. They brought a sense of relief, a sense of the peace that comes from understanding, because the first and most important lesson that these normal comets teach us is a lesson in universality. They show us that the laws of nature we observe here in our own small home are the same laws at work in the most distant places. 3i Atlas was a comet, and it behaved exactly like a comet. It was made of ice and dust materials we know very well. It sublimated under the heat of the sun, creating a coma and a tail according to physical processes we can describe with mathematics. Its brilliant blue color, as magical as it seemed, was the result of a familiar quantum dance of carbon, and its path was perfectly governed by the law of universal gravitation. Why is this so important? Because it shows that we are not an anomaly. Our solar system is not a special oasis with its own set of rules in a completely alien universe. We are part of a larger cosmos, a cosmos that is consistent and orderly. It's like traveling to a distant country and realizing that though the language and culture may be different, the chemical principles that create water or the physical laws that make an apple fall are exactly the same. Atlas and Borisov showed us this on a cosmic level. The recipe for making a comet in their home star systems was not so different from the recipe here. This lesson brings a profound sense of connection. It makes the vast and seemingly intimidating universe a little more familiar, a little more understandable. It tells us that we can use our knowledge, the scientific tools we have developed, to understand what is happening in places we can never hope to set foot. Science truly is a universal language, and in that universality, there is a beauty and a comfort. It is like a whisper from the cosmos saying, "You are on the right path. What you have learned is real. Your foundation is solid. Keep exploring." 3i Atlas was an affirmation, a confirmation that order exists amidst the chaos. It is the solid ground, the safe harbor we can stand on before we look up at the greater mysteries. It gives us confidence. Confidence in our models, confidence in our physical laws, and the confidence that our journey of discovery is meaningful. That is its legacy, a gift of clarity, connection, and familiarity, a reminder that even visitors from the most distant places can bring with them a sense of home. If 3i Atlas brought us the comfort of an answer, the confidence of confirmed knowledge, then Oumuamua brought us a completely different gift, a more difficult, more challenging gift, but perhaps in the long run, an even more precious one. The gift of a question, the gift of doubt. The second lesson, the lesson from the first messenger, is a lesson in humility. Oumuamua arrived, and in a few short weeks, it gently shattered many of our assumptions. It was like a strange wind blowing through a tidy room, disturbing everything, forcing us to look again at what we thought we knew. It challenged our understanding of how natural objects form with its impossible shape. It challenged our understanding of cometary behavior with its mysterious silence. And it challenged our understanding of the laws of motion with its invisible push. The lesson Oumuamua teaches us is one that science and every individual must always remember. We do not know everything. The universe is under no obligation to fit into the neat little boxes we have created for it. It is under no obligation to follow the scripts we have written. It is always bigger, stranger, and more diverse than we can possibly imagine in our philosophies. Oumuamua is a powerful reminder that just because we have never seen something before does not mean it cannot exist. We had never seen a natural object with a 10-to-1 ratio, but Oumuamua existed. We had never seen a comet that was inactive at such a close distance, but Oumuamua existed. We had never seen an object with a push but no obvious outgassing, but Oumuamua existed. It is an anomaly, and in science, anomalies are the most precious things of all. They are not errors to be discarded. They are treasures, because they are where real discovery happens. They are the cracks in the wall of our knowledge where the light of a new understanding can shine through. They are the questions that force us to think deeper, to be more creative. Oumuamua forced us to stretch our imagination. It pushed scientists to conceive of entirely new types of objects like hydrogen comets or nitrogen shards. It forced us to reconsider our models of planet formation and the evolution of small bodies, and it also opened a dialogue in a serious and scientific way about the possible existence of technological relics out there. It made an idea that was once taboo into a valid scientific question, a growing field of research. It gave us permission to dream with rigor. The lesson from Oumuamua is a lesson in openness. Be ready for the unexpected. Be ready to admit that our models may be incomplete, that there are still unwritten chapters in our book of physics, and always keep a curious mind, a mind that is willing to ask questions, even when those questions seem difficult or uncomfortable. It is the antidote to intellectual arrogance. It whispers to us, "You have learned so much, but an entire ocean of the unknown still awaits. Keep diving deeper." And that is a profoundly important message, a message that keeps science alive and ever moving forward. We have a lesson in familiarity and confidence from 3i Atlas, and we have a lesson in strangeness and humility from Oumuamua. One is the answer, the other is the question. One is the solid ground, the other is the mysterious, starry sky. They seem like two opposite extremes, two contradictory messages, but perhaps the greatest lesson, the final lesson, lies not in either one. It lies in the existence of both. The final lesson is a lesson in balance. Imagine the universe as a giant book, and we are the readers. If every interstellar visitor we met were like 3i Atlas, if everything were familiar and explainable, that book would become boring. We would quickly conclude that we understand almost everything. Science might become complacent, and our curiosity might fade. We would have order, but we would lack wonder, the motivation to turn the next page. Conversely, if every visitor were as mysterious and anomalous as Oumuamua, if nothing followed the rules, we know that book would become chaotic and incomprehensible. Science would become powerless. We would have no foundation to stand on, no rules to hold on to. Every new discovery would only add to the confusion. We would have wonder, but we would lack understanding, the ability to connect the ideas. The truth is, the universe did not send us one or the other. It sent us both. It sent us Atlas to say, "What you have learned is true. Your foundation is solid. Your foundation is very solid." And it sent us Oumuamua to say, "But never think that foundation is everything. There are still so many floors you have never seen." One reinforces our knowledge, the other fuels our imagination, and we need both to have a complete picture. We need both for our journey of discovery to be whole. Science, much like life, thrives in the balance between order and chaos, between the known and the unknown, between confidence and humility. Atlas is the firm ground beneath our feet, allowing us to stand firm and not get lost. Oumuamua is the distant stars we look up to, urging us to keep reaching, and we the explorers stand in the middle with our feet on the ground and our eyes on the sky. That is the posture of discovery. This final lesson is a lesson in diversity. The universe is not a monolith. It is not a mass production factory. It is a craftsman's workshop where each star system, each star, creates its own unique products with their own stories. There are familiar things. There are strange things. There are things in between. And there are things for which we do not even have words yet. And that is a wonderful thing. It ensures that our journey of discovery will never end. There will always be a familiar beauty to comfort us, and there will always be a new mystery to challenge us. That is the legacy these two visitors have left behind. A complete symphony made of both the notes we recognize and the notes that make us stop and listen closely. We have contemplated the individual lessons that each visitor brought. But when we take one final step back, we see that the story of these three encounters is not just about the objects, it is also a story about ourselves. It is a record of the evolution of our understanding in a completely new field of science, a mirror reflecting how we confront the unknown. In this final chapter, let us look back at that journey of discovery. Chapter 8. The Legacy of Questions and Conclusion. Let's go back to 2017 before Oumuamua. The field of interstellar object studies was virtually non-existent. It was just a theoretical possibility. We had no data, no experience. We were looking at a blank page. Step 1. Oumuamua and the confusion. The arrival of Oumuamua was like the first stroke of ink on that page. But it wasn't a clear straight line. It was a blot, a strange, incomprehensible shape. It threw us into a state of confusion and reaction. The race to observe it was a desperate one. Hypotheses were put forth hastily, trying to explain a bizarre and unprecedented data set. Oumuamua represents the first stage of all scientific discovery, the stage of chaos and fundamental questions. The "what is this" stage. It showed us that we don't know as much as we think we do. It shattered our complacency and forced us to admit our ignorance. This stage is crucial because that admission is the first step toward wisdom. After nearly 2 years immersed in that confusion, we entered the second stage, Step 2. Borisov and the reassurance. The arrival of 2I Borisov, a classic comet, brought a much-needed clarity. It was like after seeing an abstract shape, you suddenly see a clear drawing of a tree. Borisov gave us a reference point. It confirmed that our basic models of comet formation are correct. It brought order to the chaos. This is the second stage of discovery, the stage of confirmation and foundation building. The so this is how it works stage. Borisov allowed us to build a solid foundation, a standard model for interstellar visitors. It transformed the field from a curiosity into a systematic science. And then, with a foundation established, we were ready for the third step, Step 3, Atlas in the depth. The arrival of 3I Atlas no longer caused confusion or simple relief. It brought depth. Because we had a standard model from Borisov, we could start to compare and look for subtle differences. The brilliant blue of Atlas, its carbon richness, showed us that even within normalcy, there is an incredible diversity. This is the third stage of discovery, the stage of refinement and detailed exploration. It works like this, but why is it a little different here? Stage. Atlas took us from just identifying objects to truly starting to understand the processes that created them. It opened the door to interstellar comet archaeology, confusion, confirmation, and depth. Those are the 3 steps in the evolution of our understanding led by 3 visitors. This story is a perfect example of how science works. It is not a straight path to the truth. It is an iterative process of observing, hypothesizing, being confused, finding clarity, and then using that clarity to explore deeper layers of complexity. These 3 visitors didn't just show us what the universe looks like, they showed us what the process of learning looks like. The evolution of our understanding from confusion to depth was driven by 3 chance encounters in less than a decade. This raises an interesting question. What will happen when these encounters are no longer by chance? What will happen when we move from passively waiting for visitors to actively finding and cataloging them on a massive scale? The answer is being built right now on a mountaintop in Chile. The future of the hunt for interstellar visitors is about to begin. Welcome to the Vera C. Rubin Observatory, an engineering marvel that is about to completely change how we see the variable universe. Unlike telescopes that focus on a single object, Rubin is the ultimate sky surveying machine. With its giant 8.4-meter mirror and the world's largest 200-megapixel digital camera, it is designed to do one thing: image the entire southern sky every few nights. For 10 years, it will create a high-resolution digital film of the universe, recording everything that changes, everything that moves, everything that explodes. For the hunt for interstellar objects, this is a revolution. Oumuamua, Borisov, and Atlas were all relatively bright objects. We nearly missed Oumuamua. How many fainter, smaller objects have passed by completely unnoticed? The Rubin Observatory, with its incredible sensitivity and constant scanning cadence, will miss nothing. It will detect interstellar objects when they are still very far out in the solar system, when they are still extremely faint points of light. Scientists predict that Rubin will not just discover a few visitors. It is predicted to discover tens or even hundreds of interstellar objects every year. The era of single discoveries will truly be over. We will move into the era of statistics. We will no longer have to debate based on a sample of 3. We will have a catalog of hundreds, thousands of visitors. And with such a large catalog, we will be able to answer one of the most important questions Oumuamua posed. How truly anomalous was it? We will be able to calculate the true ratio of Atlas-like to Oumuamua-like objects. If we discover 100 normal interstellar comets and not a single other object as strange as Oumuamua, then we could conclude that it was indeed a statistical anomaly, perhaps a very rare type of natural object, like a nitrogen shard. But If Rubin discovers that for every 100 visitors, there are 1 or 2 objects with similar strange characteristics, an extreme shape, no outgassing with a push, then the story would be completely different. That would suggest that there is a whole population of Oumuamua-like objects wandering the galaxy. And if that were true, then the hypothesis of a technological origin, while still controversial, would become much more worthy of serious consideration. The future of interstellar object research is a partnership between 2 types of instruments. First are the wide-field hunters, like the Rubin Observatory, responsible for detection and early warning. And second are the analyzers, capable of zooming in on the details like the upcoming extremely large telescopes ELTs with their 30-40 meter mirrors. When Rubin discovers a new visitor, a global alert will be issued, and the ELTs will be able to turn towards it, obtain high-resolution spectra, and analyze its chemical composition with a detail that we can currently only dream of. We are on the cusp of a golden age in the exploration of interstellar visitors. The book that Oumuamua Borisov and Atlas began to write is about to get many new chapters. And the big questions they left behind may soon have answers. We have come a long way, from the hasty arrival of a mysterious messenger to the familiar greeting of a classic comet, and finally to the profound confirmation from a blue beauty. We have seen our understanding evolve from confusion to reassurance to a more nuanced understanding. And we have looked toward a future where these encounters will no longer be rare events, but a constant stream of data, a continuous dialogue with the cosmos. As we look back on the entire story, a simple yet profound truth emerges. 3-eye atlas arrived as an answer. It came to reinforce our knowledge, to confirm that the laws of nature are universal, to give us confidence in our scientific foundation. It is the solid ground. And we need both. Oumuamua arrived as a question. It came to challenge our assumptions, to point out the limits of our knowledge, to force us to be humble and to expand our imagination. It is the distant stars. We need the answers so we are not lost in ignorance, and we need the questions so we do not become complacent in our understanding. The journey of human discovery, much like the evolution of the universe, thrives in the delicate balance between order and chaos, between the known and the unknown. The final legacy of these visitors is not about comets or asteroids. It is a lesson about the very nature of inquiry. Thank you for joining Cosmic Drift for this dialogue. Thank you for taking the time to contemplate both the comforting answers and the challenging questions. As you fall asleep tonight, think of your own journey of discovery, your own book. In life, there are things you know for sure. These are principles, values, familiar people. These are your atlases, giving you the confidence and a solid foundation to stand on. There are also things you do not understand at all. The big questions about the future, about meaning, about things beyond your control. These are your Oumuamuas, forcing you to be humble, to keep your mind open, and to never stop learning. Life, like the universe, is not one or the other. It is a balance of both. A constant dance between certainty and uncertainty, between peace and challenge. Let that harmony bring you peace. Accept that you do not need to have all the answers. Sometimes the greatest value lies in asking beautiful questions. wish you a truly peaceful night. And dreams of visitors yet unknown.